Today, I want to answer a question. What is energy? It shows up in almost every textbook, but it's actually pretty rare to have it be defined explicitly. And as we're going to see, there's actually a serious problem with the definition that shows up in most physics textbooks. So today, we're going on a quest to find the real definition of energy. Let's start by talking about why energy is so important to physicists. The short answer is, it helps us predict the future. As you may know, energy is conserved. So when two objects interact, they can only interact in a way that the energy is the same at every single moment in time. It doesn't matter if it's a planet orbiting a star, or an electron around an atomic nucleus, or even a hot pocket in a microwave. When those two objects interact, they can only interact in a way that conserves energy. So this seriously narrows down the list of things that can happen when two objects interact with each other. Electrons can only orbit atomic nuclei in very specific shapes. Planets can only orbit stars in ellipses. And food heats up at a very specific rate depending on what it's made of. The point is, if you know exactly how much energy each object has, you can make a pretty accurate prediction about exactly what the universe might or might not do when the two objects interact. The universe is not free to do whatever it wants. It is bound by conservation laws like energy, momentum, and angular momentum, and more. And that's great for us physicists, because it means we can calculate what the universe is going to do before it does it. I would argue that that's actually the core of physics. Physics is fortune-telling. So that's why energy is important, but what does it do? So in our quest for figuring out the definition of energy, let's look at some examples of things that physicists typically agree are examples of energy. As I list these examples, I want you to ask yourself, what do all of these things have in common? Type number one is kinetic energy. In everyday situations, kinetic energy is 1/2 mass velocity squared. If you wonder where that equation comes from, I have a whole other video on that. A giant wrecking ball swinging down to smash a building has a whole lot of kinetic energy because it has a whole lot of mass and a whole lot of velocity. But a sculpture in an art museum just sitting around motionless has no kinetic energy at all. Even though it has a lot of mass, it has no velocity. You can think of kinetic energy as being the energy as a result of an object's motion. The second kind of energy is gravitational potential energy. In normal circumstances, it is equal to mass times the acceleration due to gravity times the height above the surface of the Earth. If I dangle a penny off the edge of the top of the Empire State Building, that penny has a whole lot of potential energy. If it's just sitting on the ground, it has virtually no potential energy. The third type is chemical potential energy. Some molecules are tightly bound together, whether that's through electrons, ions, or hydrogen atoms. When the bonds break, they release the energy stored in those molecular bonds. By the way, that's how we get energy from food. There are a bunch more types of energy that we don't have time to list all in this video, so let's just do a quick speed round. There is thermal energy, which is the energy stored in objects with a high temperature. There is elastic potential energy, which is the energy stored when a spring or rubber band or other stretchy thing gets stretched or squeezed. Electric potential energy, when you have two electrically charged objects together, such as two magnets. Torsion energy, when something is tightly wound up and wants to unwind. Sound energy, which is the energy stored in sound waves through the air. Nuclear energy, which is the energy stored in the nucleus of an atom. Light energy, which is the energy stored in little packets of light called photons. Mass energy, which is the energy contained in all things with mass, courtesy of Einstein's E=mc². Vacuum energy, which we're not 100% sure exists, but we're pretty sure it's the energy stored in empty space even when you've taken everything out of it. And it might be responsible for why the universe is expanding, and many, many more. So there are a lot of different kinds of energy, and at first they might all seem to be kind of unrelated. It's really not obvious that a speeding wrecking ball and a nutritious piece of food would contain the same abstract quantity, that being energy. So what is it that all of these different types have in common? One thing that all of these different types of energy have in common is that they allow objects to do stuff. A swinging wrecking ball with a lot of kinetic energy could demolish a building, but a wrecking ball at rest doesn't have that same ability. Similarly, a brick dangled from the top of the Empire State Building could fall down and seriously injure somebody. but a brick on the floor doesn't have that same ability. A rubber band that's been pulled back and has a whole lot of elastic potential energy could potentially knock somebody's eye out, but a rubber band sitting on a table can't. The point is, as a general rule, things with a whole lot of energy can affect the world around them in a way that low energy things can't. Things without any energy just can't really do anything. So one possible definition of the word energy is the stuff that lets stuff do stuff. This might sound like a joke, but it's actually pretty accurate. This definition was suggested to me by a fellow physics teacher, Jason Crawford. I highly recommend you check him out because he is also a published fantasy author. Links in the description. So let's use this definition, the stuff that lets stuff do stuff, as the basis for our working definition. We can rephrase it a little bit to make it a little bit more precise and a little bit more scientific sounding. So right now our working definition of energy is the abstract quantity that helps us predict how a system behaves and or interacts with its surroundings. So is that the definition of energy? No, not yet. There are a few details that we need to add in, which we will do in the next chapter. The problem with our current definition is that it's a little bit too vague. So earlier I mentioned linear momentum and angular momentum. Those are also abstract quantities that also help us predict the behavior of a system, but momentum is not itself a kind of energy. Angular momentum and linear momentum are just their own thing. So let's add to our definition that energy is a scalar quantity. Linear momentum and angular momentum are both vector quantities. In other words, you need to have an amount of momentum and it needs to be pointed in a certain direction. So if you're doing calculations with momentum, you need to carefully keep track of what direction your momentum is pointing, otherwise you'll get the wrong answer. Energy is a little different. Energy doesn't have a direction, it's just a number on its own. So a vector is something that has both direction and magnitude. A scalar is something that's just a number with no direction. So we should add to our definition that it is not just any abstract quantity, it is a scalar quantity. The second thing we should add to our definition, as mentioned earlier, is that energy is conserved. There are plenty of scalar abstract quantities like distance or speed or temperature, which help us predict the behavior of a system, but they are not themselves kinds of energy. So notice how even though kinetic energy is written in terms of velocity, velocity is not itself a kind of energy, because it's not part of a greater conserved system. Similarly, temperature and thermal energy are not the same thing, because thermal energy, even though it's related to temperature, is part of a conserved quantity, that being energy. And so I think it's very important to put conservation in the definition. We should also include the fact that energy is conserved in our universe, because we could hypothetically imagine a universe where energy is not conserved. More on that later. A third thing we should note in our definition of energy is that it comes in many different distinct forms. So I mentioned how the food stored in chemical bonds looks, feels, and acts very differently from, say, the kinetic energy of a wrecking ball. In terms of physics, we say that these two types are what's called qualitatively different. In physics, the word qualitative means general and overall even when we don't need to look at the equations. We don't need an equation to know that a speeding wrecking ball and a nutritious salad have two very different kinds of energies. So we should include in our definition that energy comes in many distinct qualitatively different kinds. Including this in the definition of energy is a really good idea because it rules out abstract quantities like electric charge, lepton number, and baryon number. Those are also abstract scalar quantities that are also conserved, but they can't switch between many distinct qualitatively different forms the way energy can. So our current definition of energy is it is a scalar quantity that is conserved in our universe, that can transition between many qualitatively distinct formats, which helps us quantitatively describe the behavior of a system and or its interactions with its surroundings. Now, just to be clear, I use the second term, quantitative. Quantitative is kind of the opposite of qualitative. It means the exact number as calculated by an equation. So the beauty of kinetic energy is it doesn't just generally tell us about the mass and velocity, it tells us specific, exact numerical constraints on what the mass and velocity can be. So this definition of energy is almost complete, but there's one kind of energy that messes it up. We're going to explore this very special kind of energy in the next chapter. What if I told you that there's actually an exception to conservation of energy? So when you have a region of empty space and you take everything that you can out of it, you have a vacuum. But there's still energy there. It's called vacuum energy, the energy left over when you've taken out everything you can from it. As far as we're aware, the density of this vacuum energy is always constant and always has been constant. But that being said, the universe is expanding. So if I had some region of the universe with some amount of vacuum energy, over time that region will expand and get bigger. So there's more volume. But the density of that vacuum energy is going to be the same. So same density multiplied by a larger volume, that's a larger amount of energy. In other words, the amount of vacuum energy in a given region grows as the universe grows. This is the one-time conservation of energy does not apply. But that doesn't mean that we should just abandon our definition. There is a way to save it. We can change the conserved part of our definition to say energy is conserved across a boundary. So what I mean by that is, imagine again we have some sort of box made of flexible material. Now there might be particles inside with energy. If we want to add kinetic energy to these particles, for example, we would have to transfer kinetic energy from something outside of the box, and it would have to go through the lid, through the surface, and inside of the box. So in other words, the amount of kinetic energy added to the system is equal to the amount of kinetic energy flowing through the boundary. You only get out what you put in. Now, over time, this box will expand due to the expansion of the universe because of the vacuum energy. And so energy would increase, but the amount of energy flowing across the boundary would remain constant. Vacuum energy is a little different because it doesn't move from place to place. It doesn't flow. It doesn't go across the boundary. So by adding that energy is conserved specifically across a boundary, we're back in the clear. In other words, the kinds of energy that can move from place to place or be transferred between objects is conserved. Vacuum energy, which is just located at one place and doesn't move, is not conserved. So at the beginning of the video, I asked a question. What is energy? Personally, the definition that I think is the best is, it is a scalar quantity that is conserved across a boundary in our universe that can transition between many qualitatively distinct forms, and which quantitatively describes the behavior and/or interactions of a physical system. I really like this definition of energy because it's just so practical. It tells us why energy is useful. That is, it describes how a system works and what it does. Kinetic energy tells us about the motion of a particle. Chemical potential energy tells us about the molecular structure. Elastic potential tells us about how stretched or squished something is, and so on. And since energy is conserved, we can mathematically predict what the universe is going to do before it even does it. And again, fortune telling is at the core of physics. Now, there are actually two other definitions of energy that show up all the time in physics textbooks, but I think that both of those definitions are actually wrong. Now, you're probably wondering, well, if they're wrong, then why do textbooks constantly use them? We'll be discussing all of that and more in my next video. Thank you so much for watching until the end of the video. If you enjoyed this new style of video, please let me know in the comments and I will be sure to make lots more of these. And if you have any physics-related questions, go ahead and ask them in the comments, and I might make a video in the future answering your question. If you learned something new today, why not leave a like? Have a great day, and I will see you in the next video.